Okay, so then by theorem 5, the followers. Hey, I probably should make this bigger so you guys can actually see all my little mistakes. There we go. It follows that there exists an n in the natural numbers such that k is equal to n times the order of a. That makes sense? That's what theorem 5 says. It's if and only if it goes both directions. So k equals n times the order of a. K is odd. Since k is odd, tell me about n times the order of a, even or odd. Yeah. Now, tell me about numbers. When can you get an odd answer if you're multiplying two integers together? So what's your conclusion? The order of A is odd. And there's your proof. It's kind of short.
Small.
It's actually a lot shorter than what I did the first time around. I totally forgot about theorem 5 the first time around.
We're glad you remembered.
I read it off of you guys' papers as I was going through. I said, well, that's a handy theorem.
You're welcome.
That's a good thing. Okay, so number 5. Think about number 5 now. I'm going to type up the theorem statement, but see if you guys can prove it in your group.
Oh, I'm completely looking at that.
I didn't specify on this one. Yeah, I'm betting you can probably use theorem 1 on that. Probably. I did that one when I did it by brute force. It only took a couple lines. Yeah. You just actually compute it. So let's go get this stuff up here. It's the same stuff. Oh, it didn't work. Let's try again. Control C. So let A, B, and C be elements of some group for any group G. And then what we're going to do is we're trying to show that the order of A inverse is the same as the order of A. So let's give the order of A a name, and we're going to call it N. Apply theorem 1, part 3. And theorem 1, part 3 simply says that A inverse to the N is equal to A to the N inverse. But what is A to the N equal to? Yeah, the identity. N is the order of A, so that becomes the identity. What's the inverse of the identity? The identity. So the order of A inverse I know is going to be less than or equal to some value N. N right here gives me, it is a value that's gives us the identity. Do you guys see that? Now we have to show it is the smallest value. we show it's the smallest value? Take any other value and show it's greater than or equal to n. So let k be in the integers such that a to the minus 1 raised to the k equals to the identity. Then what happens? What we're trying to show something about a to the k. Let me show you. So you have a inverse to the k is equal to a to the minus k according to our little theorem. I'm going to put an e equals right here at the beginning. But so if I multiply both sides by a to the k, then what do we get? Yeah, that equals to the identity. So what does that tell us about k? Notice I said a to the k has to equal to the identity. So k has to be greater than or equal to n by definition of the order of a to the k, of a. So n is the smallest positive integer that has this property. So that means n equals to the order of a inverse. Any questions on that? Lots of things to practice on that. No, what was the last one I was? Oh, we don't have to worry about number 6. It's just number 6 is actually really short. If you look at the hint, it's one line after the hint. You can play with that on your own. But what we want to do next is to look at the review. On the review, what you need to know, let's compile it. Makes it bigger. Be able to work all the examples from the reading. I'm not going to have stuff that needs other examples, but you're going to have some need to know those basic examples for when things are groups, when things are not groups, what is associative, what is commutative, that type of thing. The book gave lots of examples, so know those examples. You're going to see some of those examples on the test. Theorems. Know all the theorems and their proofs from the reading. This includes Cayley's theorem. I'm going to give you part of Cayley's theorem. It's going to be on the test. It's such an important theorem that you really do need to know it. And what did Cayley's theorem say? Cayley's theorem. Every group is isomorphic to some group of permutations, a group of permutations. And they specified how to choose it in the theorem, in the proof of it, which is why it looks so long. In reality, it's not really that long of a proof, but they have to figure out what group of permutations, they have to show it's a group of permutations, and then they have to show the isomorphism for it. So there's 3 basic steps, and within those you have several steps. I'm going to give you part of that for the test. Make sure you can prove Cayley's theorem. It's very important. And if you recall the history around it, abstract algebra started as groups were just groups of permutations. That was the only thing people studied. And then it changed. Then along came Cayley, and he said, you don't really have to change. Everything is just isomorphic to a group of permutations. So if you understand the group of permutations, you understand everything about groups. That's what Cayley's theorem says. Very powerful in that way. So, and then as far as your homework, this only comes from your homework, and it includes most of your homework problems. Because when I wrote this review, I had those homework problems as candidates for test questions. And those of you who recall from set theory and logic or other classes, not the entire question will show up on the test. Part of it will. So make sure you know how to do all of the homework problems, but you're not going to see all of them on the test. I have to pare it down, and you'll have choices. A question will have 2 to 3 options for you to choose from. You tell me which one you want graded, and I'll grade that one, even if you try them all. But it's just going to be part of one of these questions, so make sure on the test you read carefully which part of that question I'm asking. And if you don't remember the question, you might be able to ask me, and I might be able to jog your memory as to which homework problem it's similar to. And having said that, here's what the test looks like. Be able to do all the computation problems from your homework. We have 2 or 3 problems on the test that are computation only, and these would be finding, F composed of G or something like that with permutations, or F inverse, or some of those basic computation problems. Be able to show that something is an abelian group. So if I give you a set and an operation, be able to show that it's a group. You've got to be able to prove a group. That's the only one you're not going to be able to choose on. You have to prove that something is a group. A group, and I haven't decided whether it's going to have the abelian property in it or not. Yeah, is it commutative?
Oh.
So it's just one extra step on it. Be able to show that something is a subgroup. And remember that you only have to do 2 things for that. You have to show closure, and you have to show the inverses for a subgroup. So be able to show that something is a subgroup. Be able to prove properties of groups and subgroups. In other words, kind of like some of the stuff we were doing here, but we have talked about if you know your group is abelian, then the inverses in the group are abelian, or stuff like that. So given some property of the group, can you prove some property of elements of the group? And we have done a couple in class, and you've done a few on your homework, so be able to do that. And if you look in the section titles of the homework, it'll say properties of groups or properties of, operations or something like that. So be able to do that. Question?
When you're talking about subgroups, you're saying closure. Is that using onto, or is it?
No, onto is to show something is permutation. It has to be 1-to-1 and onto. Closure means that if you operate on 2 elements, your answer is back in your group. So if you're looking at the set of even numbers under multiplication, even times even is even, you're back in your group. Yeah. Be able to manipulate permutations. So if I want you to do function composition of your permutations, be able to do that. That goes with your computational problems. Be able to prove properties of permutations. And those are both from the chapter discussions. That would be what happens in class, and from your homework. So anything that we did in class or in your homework, be able to do those. Again, those are some of the basic properties of permutations that we had talked about, 1-to-1 and onto. Be able to show that 2 groups are isomorphic. You will have to figure out what function to use to do this. So get some practice, look at the basic isomorphisms that we have talked about, see how we chose the functions, try and, think in your mind what you would do to try and set up a function to be able to show isomorphism.
It's like the last class when we were looking at
The similarities of the sets. I would know how to determine if it's isomorphic and how not to determine. You have that in your notes. That's just something I would know. And then be able to determine if 2 groups are or are not isomorphic. So I'm going to give you, just like we did in class last time, are the 2 groups isomorphic? Are they not isomorphic? If they aren't isomorphic, why not? If they are isomorphic, what is an isomorphism for them? So be able to give the isomorphism. That's computational problems.
So a good part of this isn't proofs.
There's 1 page that's computations, and there's, right now I have 6 or 7 pages of proofs, so that's going to get shorter. As I said, it's all the problems.
The isomorphism one, would we need to be proving that, or showing if
That
they're
would be-
isomorphic, then state what the function is?
Two ways are on the test right now. One of them is, if it is isomorphic, what is the function? And the other one is, given that it is isomorphic, prove it.
Oh, okay.
So I will give you the function in that case, and you just show that it's an isomorphism. Yeah. So that breaks it up. It will get shorter between now and Tuesday. It has to get shorter. I don't know what it's going to turn out to be yet. Right now I have pretty much everything on the test grouped into these types of problems and these types of problems, and I have to go through and pare that down and make it something you can do in about an hour. Well, 45 minutes is what I'm shooting for. That way you'll have half an hour to play with.
How many proofs do you have to do?
Probably 4. That's usually what I shoot for in an hour. 4 to 5, depending on how long the proofs are. They're relatively short, 5 of them. But if you're proving a group, that could be a longer proof, because you have to prove, if it's an abelian group, you have to prove 5 properties, because you have to prove closure, you have to prove associative, you have to prove the inverses on it, and you have to prove abelian properties on it. So you have a lot to do to prove an abelian group. On the flip side, if I make it something very simple, then it'll be just little short, tiny little proofs for each section. So those are all trade-offs. But that's what I would know. You guys have most of this in your notes. Your extra credit question is going to be very, very similar to what you have in your notes, to what you've seen already, but not identical. Yeah?
Are we going to have to memorize theorems?
No, you don't have to give me theorem numbers or anything. You just reference them by the theorem in the book and kind of sort of explain what you're talking about. You have to remember them. I'm not going to actually ask you to state them unless I ask you to state Cayley's theorem, because that's one that's named, or the division algorithm. That's a named one. But if it doesn't have a name, there's no way I can get you to remember which one it is that I was talking about. So I would definitely know Cayley's theorem. It's very important. You can't take an abstract algebra class and not know Cayley's theorem. Well, you could, but it's not wise. Okay, we are done for today.